Okay, so let's officially start. Hello, everyone. Welcome to episode 60 of Warsaw Quantum Computing Group meetups. My name is Paweł. I'm also the organizer of these events, and today I'll be also a speaker. And I will give an introduction to quantum computing, and I'll also try to introduce the ecosystem of quantum technologies in Poland. So this is the first inaugural meeting of the academic year 2024-2025. So based on the identifier of this episode, you may guess that we started our meetups already some time ago. So at the beginning, I will try to tell a bit more about this meetup. But first, we'd also like to thank our strategic partners for supporting us. So Novero R&D, Onyx, Cogit, Quantum.io, and ThinQubit. And we'd also like to thank our honorary partners who also help us in promoting our events. Okay, so this is the agenda for today. So first, I will tell you a few words about the Quantum AI Foundation, which is the formal organizer of this event, and about our Warsaw Quantum Computing Group. Then I will give an introduction to quantum computing. I will introduce the basics, the theoretical basics, and later I will tell about some potential applications of quantum computers. Then I will introduce the state of quantum computing domain. I will tell about the recent progress and some obstacles on the road towards quantum supremacy. And finally, I will tell about building a quantum computing ecosystem, especially here in Poland. And finally, hopefully there will be some time for Q&A. So I expect that this talk will take about 80, 90 minutes. So let's start. Oh, maybe one more thing. If you have any questions, please post your questions on the chat, and there will be breaks, short breaks between different sections of this talk, and then I will try to read the questions and answer them. But there will be also Q&A session at the end, as you can see in the agenda. Okay, so now a few words about the Quantum AI Foundation. So it's a non-profit organization that I established already about 5 years ago with the aim to support education, research, collaboration in new technologies, especially AI and quantum computing, but also other fields of math and computer science and other domains. And we aim to achieve this goal by organizing these meetups of the Warsaw Quantum Computing Group. We also organize workshops on quantum computing and programming, starting from the introductory level to intermediate level, and hopefully in the future, we will be also able to organize advanced level workshops. We also organize hackathons and quantum computing contests. We release a monthly newsletter and so on. I'm currently the chairperson and the founder, and we also have the advisory board. Okay, so we started organizing this Warsaw Quantum Computing Group meetup already in 2018, so actually before the foundation was established. So it's a meetup for quantum computing enthusiasts in Warsaw. But since the pandemic crisis, most of the events are online, so everyone can join. You do not have to be in Warsaw. But from time to time, we also organize on-site events in Warsaw. The goal is to facilitate education and research collaboration of people interested in quantum computing, build the quantum computing awareness and community of quantum computing specialists. Each meeting consists of a lecture given by a quantum computing specialist. Some of the lectures, the on-site lectures, are followed by the after party, but not the online lectures, unfortunately. But of course, if there is interest in having some discussions after the talk, we can do it. Initially, these meetings were organized in several locations in Warsaw, but as I said, from 2020, these meetings are usually online only. But we also have one or two on-site meetings per year. Most of these meetings are recorded, and the videos are already available on our YouTube channel, so you can also follow them. Yeah, so here you can see some other useful links, like links to the website of this meetup with the list of all the meetups that we've organized so far. You can join our groups and follow our profiles to stay up to date. And I will later also share the slides that we will have direct access to the links. All right. Now about the quantum computing. So the first question is, what the quantum computing actually is. So the simple answer is that these are computations according to the laws of quantum mechanics, but in both the quantum computing term and quantum mechanics term, we have the word quantum. So what does the word quantum actually mean? And here I cite Wikipedia, but only because the explanation there is quite good, in my opinion. So in physics, a quantum is the minimum amount of any physical entity involved in an interaction. And the fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. And this means that the magnitude of the physical property can take on only discrete values consisting of integer multiples of one quantum. So when we talk about computing, we can talk about the algorithms, we can try to prove their correctness or assess the time complexity. But at the end of the day, we would like to implement our algorithms. We would like to implement our algorithms and run them on actual physical computers. And these physical computers are governed by the rule of physical world, which is quantum at the bottom. And we know it at least from the beginning of 20th century, when the famous Max Planck's postulate was announced, was formulated, and it basically says that the electromagnetic energy could be emitted only in quantized form. So here we have the formula where we have the energy of the photon or electromagnetic wave. There is a Planck's constant, and there is a frequency of a photon or electromagnetic wave, and n is just the integer number. So there are only just some portions of energy that can be emitted here. So this observation gave a beginning of the quantum mechanics, and of course there are some very important consequences. One of them is also the Landauer principle, which says that there is a minimum possible amount of energy required to analogically irreversible manipulation of information, like erasing one bit of information, and here you have the formula. So here, this time the Boltzmann's constant is involved, and there is a temperature of the environment. So we should keep in mind when we perform computations that our computations are governed by the rules of the physical world. And it has some consequences. So more than 60 years ago, people already observed that computing elements are becoming smaller and smaller. So if you know the history of computer science, you probably know that in the 50s of the 20th century, computers were still very large, so they occupied large rooms. So there was a natural question whether computers can be made smaller. And Richard Feynman, a famous physicist, a Nobel Prize winner, said that there is nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. In fact, there may be certain advantages. And of course, people observe that the computing elements are becoming smaller and smaller, and in particular, the number of transistors in a dense integrated circuits also increases. And there was an observation that it doubles about every 2 years. And this observation was made by Gordon Moore, and it was later just formulated and is known as the Moore's law. And this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. But several years ago, Gordon Moore himself said, I see Moore's law dying here in the next decade or so. And Intel, the company working on the processors, also observed that the pace of advancement has slowed. So now it's not, it's doubling not once per 2 years, but once per 2.5 years, more or less. So at the beginning, in the 50s, 60s, it was a bit faster. It was once per 1.5 year, more or less. But this trend will continue for some time. But the question is if this trend can continue forever. So if this trend has to be continued for more years, then in about close to 2035, 2040, a size of a single transistor should be of a size of a single atom. And in such a scale, the transistors that we know nowadays just cannot operate as they operate nowadays, right? Because of the rules of quantum mechanics. So it's natural, and actually even now, or even about 20 years ago, it has been already becoming more and more difficult to start building smaller and smaller transistor or more dense integrated circuits. So it's already challenging, right? And the natural question is how to perform or how to continue this trend, how to perform computations in such a large, such a small scale. And at the end of the 70s and beginning of 80s, there were some ideas to employ the laws of quantum mechanics. So Richard Feynman is again considered as one of the fathers of quantum computing, not the only one, because there were some people having similar ideas before, but in particular, in 1983, he said that now we can, in principle, make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function. The ones move around, the zeros move around, and finally, along a particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no averaging. But can we do it? So that was a question posted by Feynman. Since today we have a lecture about introduction to quantum computing, and I believe that you already know that the answer is positive. So we are already able to perform some quantum computations, whether they are efficient or whether they are better than classical computers is, so these are just different questions, but there's already no question about whether we can build some quantum computers. So here on the left picture, you can see the bristlecone, which is a quantum processing unit developed by Google, and on the right cartoon, you can see the topology of connections between qubits. So each X just represents a single qubit. So here we have just the nearest neighbor connectivity between qubits in this bristlecone processor from Google. So what's the difference? What's the difference between classical and quantum processors? So in case of classical computers, as you probably know, we have bits and classical gates. So the state of a bit can be 0 or 1. The bits can just serve as inputs to our classical gates, like AND or NOT, and these gates can just compute the outputs that can serve as inputs for some other, for the next classical gates, and this is how we perform the computations. But in case of quantum computers, we have qubits and quantum gates, and there are some differences. So even when we look at the mathematical representation, so in case of a bit, the state of a bit can be just an element from the set 0, 1. So mathematically, it's something very simple. In case of a qubit, a state may be in a so-called superposition of state 0 and 1, which means that it can carry some information about 0 and 1 at the same time. And mathematically, it can be a unitary vector of the two-dimensional Hilbert space over complex numbers. So it's already, you can see it's already much more difficult. There are also some other consequences. So in case of classical computers, the state is determined. So we can know exactly whether the state is 0 or 1, and it can be changed from 0 to 1 and vice versa. But in case of quantum computers, so actually a state of a qubit is also determined. But if you want to get a value 0 or 1, we have to do a measurement which breaks this superposition. And then we just have some probabilities of getting 0 or 1 after this measurement, which depend on the qubit, so depend on this unitary vector. And quantum gates can modify qubits and can modify these probabilities as a consequence. So this is let's say mathematical representation of a qubit and a superposition of states 0 and 1. So here this 0 and 1 in this, let's say, strange brackets are our basis states. So of course we can think about them as zeros and ones, but actually it's better to think about them as vectors, and not only just arbitrary vectors, because they should form an orthonormal base of a quantum system. So we can think about them, for example, about the vectors 1, 0 and 0, 1, or some other vectors that form an orthonormal base in such a two-dimensional space. But this is a vector in a Hilbert space, which means that A and B are complex numbers. And in addition, the squares of their amplitudes are probabilities of getting 0 or 1 in the measurement. So this is the formula. And by the way, this notation is called the Dirac notation. I see a question on the chat, so maybe I'll try to answer. Let me just open our chat. Unfortunately, I cannot see the question now. I'm not sure if it was posted or maybe it was deleted. but I cannot see the question. Maybe someone would like to unmute and ask a question. Maybe this will be easier. Or maybe that was just a bug of Zoom, because I cannot see a question, but I received a notification that there was a question.
Yeah, I have one question.
Yes, yes, please.
In quantum informations, that informations can be reversible, yes or no? If information can be reversible, then how can we reverse the information in qubits?
What do you mean that the information is reversible?
Like initial to final and final to initial, like something is.
So in this sense, I think it's not reversible, because when you do a measurement, you break the superposition, and then you cannot go back to the initial superposition after the measurement. But before the measurement, you can create some other states, of course.
By the way, there is a very nice example of reversible computation in rapid single quantum flux electronics. Classical computer implemented in superconductor. There is Professor Yoshikawa talk on that. He managed to reach Landauer limit, thermodynamical limit, but he uses vortices to represent logical one and quantized magnetic flux. I will post the link to his talk on the chat.
Thanks. Thank you, Krzysztof. Thank you. All right. So, Sunil, does it answer your question, or?
Yeah, I'll share that link. It's okay.
Okay. Okay, good. Thanks. All right. Okay. Yeah. So, actually, this A and B, as I said, are complex numbers, and the squares of their amplitudes should be equal to 1. And so based on the arithmetics of the complex numbers, so it's a mathematical exercise for you. That's numbers A and B can be transformed to also spherical coordinates. So there is also one important property here, that what is really important is not the so-called phase of these complex numbers, but the difference in the phase. This is the only thing that matters. So this is this transformation. So we can also think about or define a state of a qubit using just two angles, which define a point on a sphere that is called a Bloch sphere, right? So we have 0 and 1 states at the antipodes of the sphere. So in case of classical computers, the bit state can be 0 and 1. In case of a quantum computer, the state can be any point on the Bloch sphere, actually, right? And as you will see, the quantum gates quantum gates operating on a single qubit correspond to some rotations of this sphere. So that's why we sometimes say that quantum computing is a journey on the Bloch sphere, because we just transform some points on the sphere to some other points. Okay, so now going to the quantum gates. So here are just some notable examples of the quantum gates, like Hadamard's gate, which just transformed the state 0 into the superposition of state 0 and 1, so that the probability of getting 0 and 1 after the measurement is the same, it's just 50%. There are X, Y, and Z Pauli gates, so their names correspond to the names of the axis around which we rotate our quantum states. And actually, the X Pauli gate, as you can see, correspond to something like a quantum negation, right? So the state 0 is transformed to 1, and 1 is transformed to 0. So I will tell more about it. Some gates can be parametrized, so there may be also parametrized rotation gates, as you can see. And of course, we might have quantum gates operating on more than one qubit, like CNOT is an example, right? So it operates on 2 qubits, and 1 qubit is a controller for the NOT, so this X Pauli gate on the second qubit. There's a nice property that any quantum circuit can be simulated to any arbitrary degree of accuracy using a combination of the CNOT gates and single qubit rotations. So this is one of the reasons why these gates are so important. So regarding the Hadamard's gate, it also represents a rotation of 180 degrees around the axis X plus Z, or alternatively, it's a composition of two other rotations. So this is a graphical representation of the Hadamard's gate, and this is the Hadamard matrix. So this is also another important thing, that all these operations, all these Hadamard gates correspond to unitary operations, and they are actually, when we think about the states as vectors, then these operations also correspond to linear transformations, right? So some vectors are transformed to some other vectors. So we also have matrices representing these transformations, and this is a Hadamard matrix corresponding to the Hadamard's gate. Here we have the matrix corresponding to the X Pauli gate, so it's much simpler, as you can see, and so this X Pauli gate represents a rotation of 180 degrees around the axis X in this case. So this is quantum equivalent of the NOT gate, and here we have the parametrized rotation, this time rotation around the Y axis, and here is the Pauli matrix. Sorry, this is the matrix of this rotation gate, parameterized, of course. So these parameterized quantum gates are, as you will see, are useful for quantum machine learning. I will tell about it later. Okay, but I also said that we can apply quantum gates to more than one qubit at the same time, and CNOT gate is a notable example. So actually, we can think about it as an operation in which one qubit serves as a controller. So that's why the CNOT means controlled NOT, because one of the qubits serves as a controller for the NOT operation on the second qubit. This let's say X Pauli operation is applied to the second qubit only if the first qubit is in a state 1, and otherwise it leaves the second qubit unchanged. So here we have the matrix. So in this case it's a 4-dimensional matrix. So in general, when we operate on n qubits, we are in the 2 to the power of n dimensional space. So we also need 2 to the power of n basis vectors. So in this case, these are our vectors. And thanks to that, we can just easily calculate to which vectors are some other vectors transformed using this operation. Okay, and in fact, the true power of quantum computing comes when we apply and when we operate on multiple qubits at the same time. So in this case, we have n qubits prepared as a superposition of 2 to the power of n numbers, and then we apply some other elements of this quantum circuit to all the states at the same time. And we just, let's say, so by doing this, we just modify the probabilities of getting each of these states after the measurement. And this is just an example of a still relatively simple quantum circuit, but it already has several quantum gates. So here we have 8 quantum registers. All of them are initially set to 0. So in case of qubits 3, 5, 7, we do not apply any quantum gate, so we just do the measurement. So with probability 1, we'll get the value 0 after the measurement, right? So these are our classical registers on which we just store the results. In case of qubit number 6, we have this NOT operation, so X Pauli gate. So the state 0 is transformed to state in which the with probability 1 will get the value 1. And a very interesting thing happens here when we have 4 qubits, 0, 1, 2, and 4. And then first we apply the Hadamard's gate to the qubit number 4, which was initially in the state 0. So then it's in a superposition of states 0 and 1, so that the probability of getting 0 or 1 after the measurement is the same, it's 50%. And then this qubit serves as a controller for 3 other qubits, 0, 1, and 2, that were initially in the state 0. And then we apply the X Pauli gate again. And what is the consequence? So as a result, when we perform the measurement on the qubit number 4, then with probability 50%, or at least in theory, because in practice, as I will later tell you, there might be a noise in this computation. So in practice, the distribution of the results can be a bit different. But in theory, in 50% of the cases, we should receive, or with probability 50%, we should get the value 0, and with the same probability, we should get the value 1. And because of this entanglement and applying the CNOT gate, this qubit number 4 became the controller for qubits number 0, 1, and 2. So if the result of the measurement here on the qubit 4 is 0, then in 100% of the cases, the result of the measurement on the qubit 0, 1, and 2 will be 1, and vice versa. If the result of the measurement here on qubit 4 is 1, then the result of the measurement of the cube is 0, 1, and 2 will be always 0. So actually, when we perform computations using this circuit multiple times, like 100 or 1000 times, in theory, we should receive only two results. So here, reading from 7 to 0, 0, 1, 0, 0, 0, 1, 1, 1, or 0, 1, 0, 1, 0, 0, 0. 0. So these are just ASCII code representations of the uppercase letters P and G. So my initials, and you can. So I encode two 8-bit numbers in using 8 qubits in some sense, which normally wouldn't be possible on a classical computer, or actually it could be also possible in some sense, but we would need to know how we compress the information, but this is another topic. So you can also perform a similar exercise if you want. So it was just this circuit was created using IBM quantum experience framework, to which you should also have access. So just to summarize this difference, when you have a classical computer on n bits, we can process only one n-bit number at the same time. But in case of quantum computers, using n qubits, we can potentially process all possible 2 to the power of n n-bit numbers at the same time. And there's also there's also another important difference. So in case of classical computers, the results are deterministic. So randomness is actually a pseudo-randomness. So you may have some generators of pseudo numbers. But in case of quantum computers, we may have real randomness. So the randomness that actually occur and appears in the real world. And in particular, we can easily sample from probability distributions that can be difficult for classical computers. So what is the real randomness is a bit scientific and a bit also philosophical question, because there are different interpretations of the quantum mechanics. So actually, we still do not fully know what the let's say real randomness in our world means, but we can think about it as a randomness that we can obtain in our real world. I see that there are some other questions on the chat. Yeah, so there was a question. There were some comments from Krzysztof. Thanks, Krzysztof, for this. And there was a question from Sony. How do we control the phase change on qubits while we implement these gates on quantum circuits? Yeah, so Krzysztof told how to do it from a, let's say, physical perspective on a physical hardware, but you can also think about it in terms of logical quantum gates, of course. Either you can apply quantum gates, but how to do it in practice on a real physical hardware may also depend on the technology that you apply to build quantum computers. So I will tell about these different technologies later. Yeah, so do we have more questions now? We will go to the next section, so it might be good to give you time for questions if there are any. I've already answered some questions, so I think we can go on, and maybe there will be some other questions later. It's good to know about some applications of quantum computers, like so there might be quantum cryptography, and it's also good to know about some applications of quantum technologies other than just quantum computing, like quantum communication, quantum key distribution, or quantum sensing, quantum metrology. But in case of quantum computing, quantum computers can break some classical cryptography algorithms, and I will tell about it soon. They are also, or can be also applied to solve some combinatorial optimization problems that frequently occur in different domains, from AI, machine learning, to finance, transport, logistics, and I will also tell you about some of these cases later. They can sample from distributions that are difficult for classical computers. So the Boltzmann distribution is just an example. It has applications in machine learning. So there's something like restricted Boltzmann machines, for example. And there are some approaches to quantum random number generation. So the way of generating random numbers that can be formally proved that were generated using a quantum method, quantum approach, and not classical approach. We can simulate some quantum processes, which may have applications in discovering new materials, new drugs. We can search in unstructured databases using Grover's algorithm. We can generate art, and there are some papers on generating music using quantum computers. So these are just some examples, and most of the examples applications of quantum computers usually fall into one of these domains. All right, now a bit more about breaking some classical cryptography algorithms. The problem with classical cryptography is that uh, many popular quantum algorithms are based on the assumption that the factorization problem, so the problem of factorizing large numbers, is difficult for computers. So when we have two numbers, we can easily multiply them, right? So it's not that obvious that we can do it in log n operations when n is the number of digits. The n square algorithm is obvious, of course, but we can do it. But when you have an n-digit number, then no algorithm has been published that can factor all integers in polynomial time. So polynomial of the, let's say, number of digits. But what is very interesting is that neither the existence nor non-existence of such algorithms has been proved. It's generally suspected that they do not exist. So the problem is not in the class of problems that can be solved in polynomial time. And the best published asymptotic time is the general number field sieve algorithm. So here you can see its complexity. So it's called sub-exponential complexity. But it's more than the polynomial time complexity. Yeah, and in case of quantum computers, we already know how to factorize numbers in polynomial time. So there is a Shor's factorization algorithm that was published already in 90s, and here is the time complexity of this algorithm. I heard that recently even some better polynomial time quantum algorithms were published for this problem. So we already know that this problem can be solved using quantum computer, or actually using quantum classical computer. So because this algorithm is a hybrid algorithm, so there's just a quantum subroutine which is responsible for finding a period of a long sequence using the inverse quantum Fourier transform. So this is a part here, but there is also a large classical component and something like preparation for the quantum part. Okay, so this is also one of the reasons why researchers have already started thinking about the so-called post-quantum cryptography algorithms that would be resistant to quantum attacks. And there are some ideas on how to build these post-quantum cryptography algorithms. But one of the problems is that there are almost no mathematical proofs, so we still cannot be fully sure that these methods are really safe. Okay, another application, solving combinatorial optimization problems. This can be done in two ways. So this can be done using let's say, circuit-based quantum computing. And I will also later tell more about it when I start talking about quantum machine learning. But I also wanted to tell you about another interesting approach to quantum computing, the approach that is quite controversial because some researchers, and there were some papers claiming that actually there are no quantum mechanical effects involved that should give any advantage in this case. But on the other hand, the company working on this approach, which is called quantum annealing, also claims that were able to obtain something like a business advantage for some real-world business application. So let's say there are some controversies around it, but I rather wanted to tell you about the idea behind it because I think it's very interesting. So this is called quantum annealing, and the idea is that first we prepare a Hamiltonian. So we prepare a quantum system for which the Hamiltonian is easy to prepare. So for the purpose of this talk, this lecture, you can think about the Hamiltonian as a function that for a given quantum state of a quantum system returns the energy of the system under this quantum state. And the idea is that, okay, first we start from the Hamiltonian that is easy to prepare. And we should also design the Hamiltonian that corresponds to our optimization problem, so that the global optimum of this function, this Hamiltonian, should also correspond to the global solution of our problem of interest. And of course, it's not easy to find the ground state of this problem, but the idea is that when we start from the simple Hamiltonian for which the ground state is easy to prepare, like just a simple superposition of all possible states using Hadamard matrices. And then we change the strength of a magnetic field and do it slow enough. So we slowly go from this initial Hamiltonian to the final Hamiltonian. Then if we do it slow enough, and there are even some formulas explaining how slow it should be done to do it properly, in theory, we should stay in the global optimum of our problem. So at the end, we should be able to reach the ground state, the global optimum, global minimum in this case, that could be a solution of our problem. So there are several problems with this approach. I already told you that the change of this the strength of the magnetic field should be done slow enough, and in some cases it should be done really slow to ensure that the system will stay in this let's say ground state. The other thing that this is according to the adiabatic theorem, which means that we should also do it in an adiabatic way. So this should be an adiabatic process, which does not involve the transfer of heat or matter into or out of the thermodynamic system, right? And then there is this adiabatic theory saying that or claiming that when we perform such a process and we do it, let's say, slow enough, then in theory we should stay in the global optimum. And it has been also proven, which is interesting, that this adiabatic quantum computing approach is polynomially equivalent to this conventional quantum computing in the circuit model. So there is a paper about it, which is also quite interesting. And now why we can do it, why we can perform such computations. So in physics, and in particular in statistical mechanics, there is something that's called the Ising model of ferromagnetism. So in this case, we have some variables corresponding to spin up or spin down. This corresponds to the values +1 or -1. So this can be atomic spins or magnetic dipole moments. And there is a relationship between the spins represented by couplings and also correlations or anti-correlations. And there is the objective function. So this is this Hamiltonian, the function of the, let's say, energy of the system depending on the spins, which is expressed using this Ising model formula. And here we have some linear coefficients, and we also have some quadratic coefficients, right? But on the other hand, in computer science, we also have something like QUBO, quadratic unconstrained binary optimization problem. So as you can see, this formula is similar. So the main difference is that here this xi are just binary variables corresponding to values 0 and 1, right? But you can easily see that the let's say global optima are the same of this problem. So when we are able to represent our optimization problem in this form, we can also encode it in a physical system corresponding to this Ising model, let's say. And then by changing the strength of the magnetic field, we can slowly just change the Hamiltonian. So in practice, thanks to the phenomenon that's called quantum tunneling, when we change the landscape of this Hamiltonian, and initially when we state in one global optimum that at some point will start becoming not global but local optimum, it might be possible to perform this, let's say, thermal jump and go to another local or global optimum or local optimum that can be better. So this is theory, but what I heard from different people is that in practice it doesn't necessarily work this way. But we can. What is good is that we can already do some computations using available quantum annealing hardware from D-Wave. And this is an interesting example. And here, based on this example, I wanted to explain to you how to represent some optimization problems using this QUBO, so quadratic unconstrained binary optimization formulation. So this is based on the experiment that researchers from D-Wave performed together with researchers from Volkswagen. And there is very nice and relatively easy to understand paper that is called traffic flow optimization using a quantum annealing. So what they did, so here you can see the link to the article if you want to read it. So first, the researchers built a road network. So that was just a directed graph of road segments taken from the OpenStreetMap service, I guess. And they also had routes from real GPS data. So there was a data set called T-Drive. So it was the data set of routes of taxis in Beijing. And then for each car, they added two possible options, two possible routes between the source and the destinations. And it was assumed that the cars may share road segments. it was also assumed that travel time is proportional to the square of a number of cars on a route. So this is a simplification, but it's quite realistic. And the goal is to minimize the total travel time. So how they did it, right? So let's introduce some binary variables qij. So this variable should be equal to 1 only when car I takes the route j. So each car has 3 possible routes to take, and each car should select exactly one route, right? So this formula, this equation should be true for all the cars from all I, right? So we need to ensure that this condition is satisfied. And then when we introduce a set of these variables associated with routes that share the street segment S, then the cost of traveling through this route segment S can be defined in this way, right? Because we assume that this cost is proportional to the number of cars, to the square of the number of cars taking the given road segment, right? So that's the cost of traveling through this road segment S. So if you want to get the total cost, we should just sum it up over all road segments. And this is our objective function, right? But you can easily see that the minimum of this function is just 0 when we assign the assign the value 0 to this binary variables q. But it's not the feasible solution to our problem, because then this condition is not satisfied. So actually here, this part would be, let's say, unconstrained binary optimization. And we do not want to have, let's say, additional constraints. So if we want to have this problem, keep this problem unconstrained, we have to somehow encode our constraints into a similar formula and ensure that this constraint will be always satisfied when we perform the optimization. So we can do it this way. So we just take the sum for all cars of this formula, and you can easily see that if a solution is not feasible, so that for a given car we have 0 routes or 2 or 3 routes, then this sum will be greater than 0. And if the value of this parameter is much larger than 0, is very large, then this component will start dominating over this component. And then we can ensure that the solver will not propose to us the solution for which this component is very large, because we want to minimize the sum, right? So it will not be considered by the solver as a minimum. So only the solutions satisfying these constraints will be proposed by the solver. So that's the idea. So this is a parameter that let's in some sense balance the trade-off between the probability of obtaining a feasible solution and the quality of the solution that we can get. And it's an open question on how to set the values of these parameters. But when we do it, we can see that this is again the quadratic unconstrained binary optimization problem, right? So we have only binary variables of degree at most 2. And so the researchers were able to encode it in the D-Waves machine. They performed computations. So in this T-Drive data set, they had more than 400 cars, more than 1,200 logical variables. So the space of possible solutions was astronomical, of course. But as a result, after 22 seconds, they obtained a relatively small number of streets that were heavily occupied. So that was the solution. And this is the original traffic in Beijing, based on this original data set, T-Drive. And actually, in this original paper, there was no comparison with any classical algorithm. So we cannot say that this is already a quantum advantage. So I'm pretty sure that classical algorithms should be able to find very good solutions for this problem as well. But it already demonstrated that we are already able to perform some computations on a quantum annular, which is something we should appreciate, even if it's still not the quantum advantage. There are already many companies from the logistics domain and also from other sectors that are interested in similar solutions, right? Because there are multiple anti-hard optimization problems that are difficult for classical algorithms. So it's natural to look for some quantum algorithms. So in particular, in machine learning, there are also many combinatorial optimization algorithms. So often when we train neural networks, we rather perform continuous optimization, because we just do we calculate the gradients and apply the backpropagation algorithm. But when we encode the weights of the parameters of connections between neurons, then all these weights are represented using the finite number of bits. So it's still only combinatorial optimization. So when we talk about the intersection between quantum computing and machine learning, it's good to know that there can be both the applications of quantum computing algorithms to work on classical data or on quantum data, but there can be also applications of classical machine learning algorithms to enhance and to build better quantum computers. So in the first family, so in when we think about applications of quantum computing to some classical data, there is a family of algorithms that are called variation quantum algorithms. So they share a common structure where a task is encoded into a parameterized cost function, which is represented using parameterized circuit that is called the ansatz. And this parameterized circuit is evaluating using quantum computer, and then the classical optimizer trains these parameters of our circuit in a classical way. So it emerged as the leading strategy to obtain quantum advantage on the so-called NISQ devices, so noisy intermediate scale scale quantum devices, when we still have a lot of noise in our quantum circuits. There are also some approaches to fault-tolerant quantum computers. There are some kernel methods where we can use quantum kernels to for support vector machines, for example, and this can be used for classification problems. So actually, I've already heard about some quantum approaches to most of the existing machine learning, classical machine learning techniques. There are already many papers on this. There are already conferences on this, and this domain is very interesting, but it's very difficult to prove any advantage. But actually, I've already read some papers in which the researchers claim that in the experiments they achieved some advantage just by adding some quantum layers to their classical architecture of neural networks or a support vector machine, for example. But as I said, it's not possible, or it's difficult to prove that it's really an advantage, because it's very likely that there might be just better classical algorithms that can do the same. When we can also apply classical machine learning algorithms to work on quantum data, and examples are for the quantum state tomography, which is a process by which a quantum state is reconstructed using measurements on an ensemble of identical quantum states. There's also quantum feedback control and quantum circuit optimization using reinforcement learning. And there is a nice review paper by Anna David and some other researchers from the Faculty of Physics of the University of Warsaw about modern applications of machine learning in quantum sciences. I can also tell you about another interesting application of these techniques. So here I told you about the importance of this parameter that is called the relaxation parameter. And I can tell you that there are also some nice papers about applying machine learning techniques to let's say, estimate the quality of different relaxation parameters in the QUBO formulation. So there are such classical machine learning approaches as well. Okay, time for questions, because we'll be heading to the next section. Questions or comments? So what do we have here? There are some questions from Sunil, and there are some comments from Krzysztof. So thanks, guys, for the discussion here. I do not see more questions now, so let's maybe go.
Maybe one
Yes.
question from me. Are
Yes.
you aware of existence of quantum neural network that is effectively implemented in some type of technology? Because somehow the people are quite silent about existence of quantum neural networks.
Yes.
There was a lot of promises, even by big players, but there is surprisingly no kind of progress shown. So are you
Yes.
aware of existence and the progress?
No, to be honest, this is exactly what I heard, right? So in this, despite of the fact that I know that there are multiple papers on this, it's really difficult to show any advantage, even not provable advantage. But I only heard about some approaches where we had a classical neural network, and then a quantum layer was added at the top of it, and then someone claimed that they receive the advantage. But quantum neural networks are different, because actually in quantum neural networks, we may have, or hybrid neural networks, quantum classical neural networks, some neurons can be classical, and there are just parameters on the weights of connections. But instead of some neurons, we may have this parameterized quantum gates, right? So these are the parameters that we want to train. So these are so this is one of the approaches to build the quantum neural networks, at least. So in Poland, Piotr Gawron was one of the researchers working on this, but I think that he also hasn't reported any real advantage of this architecture. And I agree with you that I also heard some opinions that people even stop believing that there will be any advantage, taking into account how powerful are already classical methods using powerful GPUs, right? So it might be really difficult to outperform GPUs in this case.
Maybe I will tell in a slightly different way.
Mm-hmm.
So quantum mechanics is linear theory essentially.
Mm-hmm. Yeah.
And quantum neural, the neural networks require certain level of nonlinearity. That's a first
Mm-hmm.
thing that is a kind of obstacle. Second thing is, let's say I have some idea on possible physical implementation of quantum neural network with use of semiconductor quantum dots. So if some of you is more interested in this topic, please contact me as by email or something like that. I will post the email on the chat. All right.
Please do it. Maybe I can tell about one more thing, because in case of this variation quantum algorithms, I also heard, because you know the contemporary quantum circuits are still noisy, but actually in case of machine learning, the noise is something that can give you some benefits, because as you are if you are familiar with classical machine learning, you probably know some regularization techniques to prevent overfitting, and one of these techniques is called the dropout, when we randomly just remove some connections or some neurons from our architectures. So in some sense, this noise in contemporary quantum computers also serve as some kind of a regularizer, right? And some people claim that this could potentially give an advantage, but then there are some counter arguments that we can even try to classically simulate the quantum noise, right? So even if we can get any advantage from this quantum noise, then we can try to simulate this quantum noise classically. But this can be possible only in some cases, and until up to some scale, because actually I will later show the slides about the quantum advantage, and I think that one of the cases in which the quantum supremacy has been showed was also related to trying to classically simulate some quantum circuits with a noise, and it's not that easy for classical computers. So perhaps at some point in the future we can get some advantage thanks to just the quantum noise that is not easy to be simulated classically. But this is just a hypothesis, right? So I just heard about such ideas, but it's hard to say how realistic it is.
Well, noise is important in the training of classical neural networks, basically. Noise, and the noise is information, by the way, and noise is a part of system dynamics, so it's not just a trash. Noise is a very important factor.
Yeah. But you know, the question is whether this quantum noise can really give advantage, right? And whether or up to which point we can classically simulate the quantum noise as well, right? So these are also some questions that are important here. Okay, let's go further to the state of quantum computing, and I will try to tell you about the recent progress. So as you can see, so here are just some important announcements given by different companies about their progress in terms of the number of qubits, but actually what is very important is not only the number of qubits, but also the quality of the qubits, the fidelity, so the noise that is related to these qubits, as we've discussed, and also the topology of connections, right? So this is important to know, that the number of qubits is not everything, right? But even when you look at the number of qubits, we can see that there is a progress, right? When you try to compare the number of qubits in computers of different key players in this quantum industry, we can see that there is some progress. So it's not as fast as in case of artificial intelligence nowadays. It's totally different order of magnitude of progress, but it seems that there is a stable progress. Recently, I participated in a lecture given by Professor Jakub Milczarek from the Jagiellonian University, and he tried to extrapolate the current pace of the progress in terms of something that is called the quantum volume, so the number of qubits times the depth of the circuit. And he said that when the current pace, or if the current pace is um, is kept, and it will have the same pace in the next years, then will not obtain quantum supremacy earlier than in about 30, 50 years. So probably we'll need to wait for some time, but this is under the assumption that the current pace will remain. But you probably also know that the advantage, or the pace of advancement in the technology is rarely linear. So usually it's from one breakthrough to another breakthrough. So it is possible that at some point this pace of advancement will be much faster. But even in the current pace, we can see that at some point in the future we should expect quite powerful quantum computers. And I will later tell about some obstacles and what we can expect. But it's good to know that currently we live in this NISQ area, right? When the quantum computers are still noisy, there's the intermediate scale with just a few hundred or a few thousand qubits with a noise, of course. Yeah, so we are still at this stage, but but even in this stage, we've already obtained something that can be called the quantum supremacy. So actually, the first announcement of in this field, or at least important noticeable announcement, was made by Google several years ago, where they published a paper in Nature, and there was a quantum supremacy using a programmable superconducting processor, and they proposed the task of sampling from the output distribution of random quantum circuits as a demonstration of quantum supremacy, right? So this is also partially related to simulating these quantum circuits. So there were some controversies. There were some discussions whether this was already approved of this quantum supremacy or not. So researchers from IBM claim that this could be still simulated on the most powerful quantum computers, but they haven't really showed it. And of course, even from the engineering perspective, it could be very difficult. But later there were also some other similar announcements made by other researchers from China and later from IBM as well. So based on that, we can just already say that this quantum supremacy have been already announced. So we can maybe debate and at which point and who was the first, but it's currently rather out of the question that we already have some quantum advantage, but of course only in some, let's say, still relatively maybe not simple, but rather artificial cases that still do not have real practical that still do not give us real practical benefits, right? So the problem of approximating or simulating the output distribution of a random quantum circuit is still not a very practical application of quantum computers. But this is something that we should acknowledge, of course. And when we talk about the progress, it's also good to know that there are different approaches to build quantum computers. So here I mentioned some of them. So actually this should be 3 dots because there are many other approaches based on what I know. And here you can see the number of qubits available on the largest. It doesn't mean that they are also the most powerful, but these are for the quantum computers that are the largest in a given domain based on just the number of qubits, like ion traps approach, superconducting qubits. There are also some semiconducting approaches. There are photoning qubits. So actually this D-wave machine, this quantum annealing machine, is also probably based on superconducting as far as I remember. So it's a different technology because as you saw, we can use it to solve only the combinatorial optimization problems, but it also showed that all problems actually can be just translated in polynomial time to this kind of problems as well. But because of this necessary translation, this number of qubits is not something that can really give us advantage at this point. But D-Wave also claimed even recently during the previous meetup of Warsaw Quantum Computing Group, there was a speaker from D-Wave, and he said that in some business applications they've already achieved some advantage, which is not provable advantage, of course, but they achieved some results that they didn't manage to achieve in any other classical way, right? So it's not a mathematical proof that some other classical approaches that are better do not exist, but they just said that okay, they computed something on the quantum annealer that people from a given company were not able to compute using the classical hardware. So basically, this is what they said. Whether this is true or not is an open question, because these results are not published, or they are rarely published, at least. And as I also told you, some researchers claim that they carefully analyze the D-Wave machines, and they do not see that there are some quantum effects that could bring the advantage. So probably this quantum annealing could be also simulated classically. But of course, there is a question whether we can do it on the existing high-performance computing platforms, or what should be the computational power, and so on. So there are many questions around this, of course. Neutral atoms is another approach, and another interesting approach is topological quantum computing. So as far as I know, such computers do not exist yet, but Microsoft was one of the companies working on this topological quantum computing approach. They collaborated with Delft, Technical University of Delft, some time ago. There were also some controversies around this, that something were, let's say, overpromised or over optimistic of what can be actually achieved. So what might be the future? So there's a famous quotation attributed to several people. The oldest person on this list is Abraham Lincoln, so I put him here, that the best way to predict the future is to create it. So this is why it's important to work in this quantum computing domain. But we should be aware of some obstacles on the road toward quantum supremacy. So the coherence, the limited quantum state duration, is one of the obstacles. This limit also the depth of the quantum circuits that we can build. The noise, so there is a need for error correction and error mitigation. So actually, what is also very interesting, that we still do not know that many algorithms for we can really prove that they can give any quantum advantage. So even in the case of the factorization problem and the Shor's algorithm, it hasn't been proven yet that this can really be the advantage, because it hasn't been proven that this factorization problem cannot be solved in polynomial time. So it's really difficult to prove some things in computer science. And from the technological point of view, building some quantum gates, it's still challenging. So I heard that in case of these photonic quantum computers, it's especially difficult. But why we should be optimistic? So there were some papers in the 90s that proving that the quantum error correcting codes actually exist at all. And it was even proven that this quantum error correcting codes could theoretically push the error rates as close to zero as we want. So according to Scott Aronson, also a famous researcher working in this domain, this was the central discovery that convinced people that scalable quantum computing should be possible at all, and that it is merely a staggering problem of engineering. So this is what Aronson said. And as for now, we believe that we should be able at some point to build the scalable quantum computers, and that this is just a matter of time, maybe quite a long time, we'll see. And this is just one of the examples of relatively simple quantum error correction codes that work only when we assume that when we have 3 qubits, then one of them can be flipped. There's only one bit flip in case of only one of the 3 qubits. So then under this assumption, we can encode a single qubit using 3 other qubits. And then when there is only one single qubit flip and we see the output, we can reproduce the initial state. We can understand where exactly was the error. So this is so there's the approach of this surface codes, error correcting codes. But there are also some other approaches to error correction that are much more difficult and more advanced. So regarding proving the advantage of some quantum algorithms over classical algorithms, this is a very interesting example. So several years ago, the same Professor Aronson gave an interesting open problem to his genius student, Ewing Tang. So she was 18 at that time, and she was already a PhD student under supervision of Professor Aronson. So there was a recommendation problem that was believed to be difficult for classical computers, but the quantum algorithms, polynomial time quantum algorithms for this problem have been already known, at that time. And initially it was believed that this problem could be an example of the quantum advantage over classical algorithms. And this was one of the tasks of Ewing Tang to prove it actually that this is the quantum advantage. But actually she came up with something else, because based on analyzing this quantum algorithm, she just proposed a polynomial time classical algorithm for this recommendation problem that was believed for decades to not be solvable in polynomial time. So this is another reason why it's important to work on quantum technologies and quantum algorithms. Even if we fail at some point, we can still discover something new. Like if we fail with building the scalable quantum computers, maybe we'll discover some new laws of physics that will just prevent us from building scalable quantum computers at some point. But yeah, as for now, we still live in this NISQ area. So now going to some quantum computing frameworks, Circu is one of these example of a Python framework for working on these noisy intermediate scale quantum circuits. So I've already told you about this quantum supremacy from Google. There is another framework that is very popular. It's Qiskit. It's a framework from IBM. So actually, currently it's open source already. It was initiated by IBM, and you can just see a simple Python code using this framework to creating something that is called the belt state, so superposition of two qubits. And sorry, entanglement of two qubits, of course, entanglement of two qubits. We have a quantum register with two quantum qubits, and then we just store the results of measurement on classical registers. And here is a similar code in case of the PyQL, which is a framework from Rigetti, is another quantum computing startup. Here is a framework code of Project Q. It's an open source project developed at the ETH in Zurich. If you want to run something with the quantum annealing algorithms, the D-Wave Leap framework is the way to go. And you can get, I think, 1 minute of computing time per month if your project is open source. So most of these libraries are in Python, but it's also good to know that there are some good libraries in Julia. So Julia is a modern programming language that is well optimized and well designed for parallel computing. So this is one of the reasons why it is also expected to be suitable for quantum computing, because we can easily parallelize simulations of some quantum algorithms, of some quantum programs. And YAO.jl is one of the most popular quantum libraries written in Julia or for Julia framework. PennyLane, this is another interesting example because this was the first library for quantum machine learning. So here you can see that there was a circuit, parameterized quantum circuit built, and this is a function for calculating the cost from this circuit, and then calculating the gradient to find the better parameters. Because this was the first library for this quantum machine learning or variation quantum algorithms, it was called TensorFlow of quantum computing until Google released its TensorFlow Quantum library. So now this is the TensorFlow Quantum from Google. In Qiskit, we also have a module for quantum machine learning as well. Yeah, so this was about the current state, and now I'll go to the topic of this quantum ecosystem, but let's see if we have some questions on the chat. I do not see more questions. There's another good comment from Krzysztof about the work of Professor Yoshikawa. So let's go further and let's start talking about quantum ecosystem. So of course, the worldwide quantum ecosystem is very large, and even the ecosystem here in Poland is already, let's say, at least moderate, as you will see. But I wanted to tell you about an interesting initiative first, in which I'm also involved, and I believe that you might be also very interested in joining. So it is called QWORD. So QWORD is a global network of individual groups and communities collaborating globally, but acting locally. So organizing different events like workshops, hackathons for their local communities. But in QWORD, we collaborate globally to develop educational materials for people and organize some educational events for people. And all these events are free for participants. So this is one of the actions that we have, that all these events should be free for participants. So of course, we can try to find some sponsors or donors to support the events, but from a perspective of the participant, this event should be free. And we have several, let's say, departments, right? So one of them is Q Education department. So this is a department in which we we organize, we work on these educational materials together, and then based on them we organize this open online workshops on quantum computing, and we have workshops at different difficulty levels, starting from introductory level, that's called Q Bronze, to more intermediate level like Q Nickel or Q Silver. So the project in which we work together in the Q Education department to develop this education materials is called Q Kitchen. And of course, as you can expect or imagine, the ultimate goal is to prepare the full quantum computing curriculum for the university courses, or even for the complete university studies. So this is important because, in many countries, especially underdeveloped countries, there are not that many resources, both human resources and financial resources, to really prepare high quality educational materials. So that's why at some point, a few years ago, we decided that it's good to collaborate globally, and it will be more efficient to just develop these educational materials together, and then they could be reusable. Maybe they could be translated to different languages and then used in different countries. But we do not restrict QWORD activities only to organizing workshops, because we also organize research or online research internships that are called Q Intern. So here the idea is that first, researchers from all over the world can apply and submit their project ideas, and then students or other researchers from all over the world can apply and declare which projects are interesting for them, and then we match, as QWORD, we match the senior researchers with let's say junior researchers, and then a tight collaboration over several weeks of the summer each year. So this year it was July, August, and each year it is during the summer, and then there is a demo day to demonstrate the outcomes. I'm also one of the mentors, and I also propose some topics each year. So this year we had a very interesting topics proposed by Jarek Duda, so a colleague of mine, and Krzysztof as well, about the two-way quantum computer. So that was quite interesting, and several research papers have been already published on Archive. I told you that we collaborate globally but act locally. So locally we have multiple local groups, the so-called Q cousins. So this is outdated a bit, because currently we already have 33 Q cousins worldwide. So these are the local groups where people collaborate and organize different events, but also participate in this global work on the education material. So here in Poland, we have the Q Poland, which was also one of the founding members, one of the 5 founding members of QWORD. I'm currently also serving as a coordinator, and there are about 20 people in Q Poland, and we work together to organize different events, like workshops on quantum computing. You can check the list of workshops that we've organized. We've already handed out more than 440 certificates for people, because after these workshops, people can get the certificates, of course. And this year, for sure, will reach 500 certificates already. We also organize joint meetups with quantum computing groups from Toronto and Washington. We also organize hackathons. So actually, in 2 days from now, we'll have the Q Poland Global Quantum Hackathon. You can still sign up by tomorrow if you are interested. There will be 5 thematic tracks, and there are some money prizes for people. And this is the 4th edition of our hackathon. So in the previous 3 years, it was focused only on the quantum games, so educational games taking advantage of quantum computing. We also organize a contest on popularizing quantum computing. So this is addressed to high school students and university students. We also organize a conference on quantum machine learning. So this is an online conference that we've organized first free edition with our Q cousin from India, with Q India. This year we organize it alone as Q Poland, but next year most likely we'll also organize it with some other Q cousins from Q World. So you can find information how to join us on the Q Poland's website. So now a bit more about the quantum computing ecosystem in Poland. So in general, it's good to know that the Polish science has already played an important role in the development of quantum computing. So even some researchers from Poland, at least two of them, are now considered as candidates for the future Nobel Prize in Physics awards. So one is Professor Jurek, another one is Professor Artur Eckert. And at least a few Polish startups and companies carry out carry out research to or create products in the field of quantum technologies. And we also have several research groups at different universities here in Poland. There are also at least a few foreign companies that have branches in Poland and that deal to some extent with research in the field of quantum technologies. So Orca Computing is one of them. Recently, IQM opened its branch in Poland. Oxford Ionics has its office in Poland as well. There are some NGOs, non-profit organizations supporting research, education, collaboration in quantum technology. So the Quantum AI Foundation that I founded and I'm leading is just one of them. We also have some VCs funding startups working on quantum technologies. There are some meetup seminars, others to enthusiasts of quantum technology. So this Warsaw Quantum Computing Group meetup is just one of them. There are some social media groups and profiles dealing with quantum technologies here in Poland. And of course, there is a large human potential and good quality of education in the field of quantum science, mathematics, and physics. So beside the Q Poland, there are also some other efforts to integrate this quantum community in Poland. So Cluster Q or Cluster Kwantowy is one of them. We also have the National Chamber of Commerce and the Technical Committee of Quantum Technologies that was created just a few months ago. And I've already heard about some other other ideas, other approaches aiming to integrate our quantum community here in Poland that is already of a moderate size. It's not that large as the AI community, but as you have seen, there are already several research groups, startups that have some successes. And if you are interested, there is a nice report that we prepared already a few years ago, so it might be outdated a bit, but anyway, I still recommend you to check it. That is called Time for the Digital Economy or Czas na cyfrową gospodarkę in Polish. And there is a dedicated section about the quantum technologies that was prepared by the Quantum AI Foundation. And this is just a screenshot of another seminar that is online and open for everyone and organized by a group of Krakow. So there is a Krakow Quantum Informatics Seminar or K quiz in short. And that will be the next meetup in October. So you can attend if you are interested. I also collaborate with them, so wanted to promote it. But of course, there are some other open seminars as well in the Polish Academy of Sciences. There's a Center for Theoretical Physics. They also have their seminars, and there's also some other seminars that are close. So regarding business or some funds, I also wanted to tell you about an interesting initiative aiming to fund open quantum projects, and it's called Unitary Fund. So actually, the grants that they can give are micro grants because it's up to about $4,000. But still, if you work on some open source projects in quantum technologies, that's something that can give you a good start at the beginning, right? So I recommend it to you. And where to learn more, you can see some links here to the website of QWord, some Facebook groups that I'm aware of. We can subscribe to some newsletters. You can find some good resources, including some open books, good books on quantum technologies on the website of the Quantum AI Foundation. There are many videos on YouTube already, like lectures of Peter Witek on quantum machine learning, or all the meetups of this Warsaw Quantum Computing Group are recorded as well. Yeah, if you're interested, let's stay in touch. I can tell you that there will be next meetup organized by us at the beginning of October. So there will be some announcements on all these groups on social media, and I also sent an invitation to our mailing group on Google Groups as well. So at the end, we'd like to thank once again our strategic partners for supporting us and our honorary partners for also helping us advertising this meetup. And last but not least, if you are interested, you can also donate our activities or just give 1.5% of your tax in Poland for the purpose of promoting or organizing these educational activities that we do for our community. So I thank you for your attention. If there are some other questions, I will be happy to answer. If we have time, we can also try to engage in some discussions. Maybe someone would like to announce something else, then it's also a good time for it. And yeah, and if you follow our profiles, then you'll be notified about the next event, of course. And of course, I invite you to actually join this Quantum Hackathon that we'll have in just a few days from now. Yeah, so you can sign up by tomorrow.
Maybe I will have one comment, if possible, right?
Yes.
So thank you for your presentation. So in my perception of your presentation is that you of course naturally coming from mathematics and computer science. That's your field, right?
Yes, yes.
But let's say I have visited Professor Fujisawa, who like 4 years ago in Japan, and the guy was the first guy that has created single electron semiconductor devices. He got controllability over single electron semiconductor devices. This was done in 2003 by him. He mentioned to me that software is easy, the quantum hardware is difficult to be done.
I agree.
And actually, in his case, it took 4 years to master the controllability over one electron wave packets. So he could announce the construction of single electron devices, the semiconductor single electron devices, famous Fujisawa work from 2003. Then there was a shift of paradigm because people went from let's say single electrons to spin-based quantum computation. And what is so in my perspective, your view on this quantum technology in Poland is rather from software perspective in that sense. So what is a kind of at least a kind of missing from certain angle, I would say, is deep analysis on future possible developments in quantum hardware experiments. And to give you a very specific example, so for example, in Poland, there is a Maciej Zgierski from Polish Academy of Science, Institute of Physics. He does superconducting Josephson junctions. Rather in a classical regime, nevertheless, he does. There is another group which is at AGH University, AGH, University of Science and Technology.
Yes.
They try to reproduce some arrays of Josephson junctions. So this is direction in terms of let's say of this quantum hardware development. Then if we talk about other schemes of then superconducting scheme for quantum hardware to be developed, then there is a famous Piętka from University of Warsaw. He does polarons liquids and this direction in direction of there is a work on quantum neural networks from in that perspective. There is a Wrocław which does quite recently, it was during this hypercomplex seminar where you have attended, in which 2024 from 14 to 18 September, there was a Gavron from Dr. Gavron from not a Gavron, there was somebody else. I'm forget. I'm sorry, I mispronounced the name.
Okay.
There was a guy on 14 September presenting array of semiconductor quantum dots. that basically implements single electron devices in a semiconductor. So there is a bunch of research centers in Poland that has certain capacity of doing quantum hardware. And actually, since I work with European Quantum Industry Consortium, in a sense, I belong to, because I have a company, Quantum Hardware Systems, and the same YouTube channel of the same name. So I try to find a potential for real construction of quantum hardware in the way that because for me just development of quantum software is not sufficient. Of course, Poland has excellent tradition in mathematics. Let's say Poland worldwide is mostly known because of by mathematicians more than physicists in general. Like in Japan, Polish mathematicians are always famous. But I would say, so there is a kind of lacking attempt to formulate this perspective of this quantum hardware development in Poland. That's what I can say. And actually, I believe we do have a potential. So we have at least 3 main centers that can do such things, like Warsaw, like Kraków, and like Wrocław. At least 3 centers have the capacity of doing it. What is the missing is the missing of a bigger plan, and actually hardware, because I mean quantum technologies from the point of view of hardware is nothing else as very delicate parameterization of quantum experiments, which is a costly by technical means. So that's how it is. I'm sorry for big long comment, but somehow
that's fine.
I'm kind of involved in this business. I try to find partners for a collaboration, and also if there is a chance, I would be happy to give a possible talk with certain perspective on such things.
We'll be very happy to host you during one of the next meetups. So the next one will be in November, and we already have plans for this, but we can try to find another date at the end of November or beginning of December for you, if it's fine. So we can later communicate by email. But
Sure.
Of course, I'm aware of let's say the fact that this quantum hardware is actually very important. As you said, it's more difficult to build, and actually, as you maybe remember from the slide that I showed, indeed most of these obstacles on the road toward quantum, something that we could call quantum supremacy, is at the hardware level. Though there are some problems with algorithms as well, but the main problems are on the hardware level. And I agree that we have great human potential. So this is what we say here. But I'm also agree that that there is a lack of this, let's say, larger plan that should be called a strategy, Polish national strategy for development of quantum technologies, because several countries, or actually not several, many countries have already developed their national quantum strategies on how to...
Like Netherlands. I was in Quantum Expo in Netherlands.
Yeah.
They absolutely organized in incredible way. Probably Netherlands are the best organized in terms of quantum industry in Europe those days. At least if you compare the size of the country, the money and everything, they are really coherent in the way.
I would say that it's very likely, at least in the European Union, when you look at Europe as a whole, then maybe UK might be more advanced, but of course they also have more resources in the UK.
Well, I would discuss because I in a sense I fall in love with Delft University achievements. That sense.
Okay, that's fine.
So, but anyway, sure.
It's even difficult to compare, but I also know that UK has also its own national strategy already. And what is a good thing, good news that maybe I can share, because I'm also a member of this Cluster Q and this National Chamber of Commerce. I know that there are already some works. Some works have started to, let's say, develop this Polish national quantum strategy, right? There are some first initial documents. So as for now, these are rather, let's say, bottom-up approaches from the quantum community. From the
Yeah,
top
but
down, yes.
but forgive me for saying, of course, we used to talk about the building of strategy and formalizing the strategy, but to be very honest, it's about ability to produce quantum chips. You need, let's say, real facilities with highly oriented people, with
Yeah,
people having ideological goals, not just
yes,
scientific goals,
yes,
to be the best in quantum chips. And this is
yes.
even more important than just having this justification by a kind of strategy law. You know what I
But
mean?
what the elements of the strategy could be to build such a center, right? And then below the strategy there is also politics, how to achieve it. But in the strategy, one of the elements could be, okay, let's build such a center, right? So actually, this was a similar thing was in the UK too. They already built something like a national center for quantum technologies. So perhaps this should be in our national strategy to have such a center, right? So this is that's something that we should discuss. But what I realized based on also discussions with the representatives of the government, it seems that we really need to try to do it from the, let's say, bottom up, with the bottom up approach, because it might be it for sure can be possible, but it definitely will take much more time if we just leave it to the top down approach and we wait for the government to just coordinate it.
You know, I simply believe that breakthrough is done by some individuals, but you need to give a power to very gifted individuals that have already certain level of achievements, like those
Yes.
individuals like Professor Dietl, the individuals as Professor Zgierski, certain individuals supposed to given 10 times more funds and a kind of freedom in action, to trigger and to make a kind of, let's say, the salary somehow depending on the achievements in quantum chip development, something like that. I mean, because we in Poland we used to say a thing via the filter of ministry points per publication, but I would say I would give money just for better quantum chip upgrade. So
Mhm.
slightly different methodology of approach.
Yeah, totally different. But I fully agree with you, and yeah, definitely, I believe that we'll be collaborating on this, let's say, national quantum strategy, hopefully, because it seems that we already have reached this critical mass. There are already many entities in both this cluster Q and this quantum technology committee, willing and understanding that we really need to to develop this quantum strategy in Poland as well. So I believe, I hope that this is a matter of time. And of course, the important thing is what should be included there, and there your ideas should be put as well, because I fully agree with them. So so I think that they are good, of course. All right, so there will be, for sure, there will be more announcements about it. Maybe anyone else would like to share something, share their opinions, their ideas, comments. All right. If not, then I think we can slowly finish our meetup. And yeah, Krzysztof, as we discussed, will later contact to
Yeah,
just
yeah.
schedule the best time for your
we
talk.
we are in touch, and also I have certain access to some documents by European Quantum Industry Consortium, so perhaps I can also refer to some, uh, to if I get a permission, I can release some of their content to public space, so I can
Okay.
inform you about certain
Yeah.
strategy of Union in that
Yeah.
direction.
Yeah. Yeah. And actually, we've also in this quantum committee, we've already collected quantum strategies from different countries as well. So yeah, definitely. But there will be a lot of work to do, and the next year is the International Year of Quantum, so there will be many things going on. Hopefully, I hope we'll manage to complete our national strategy next year. Good. I will now stop sharing my slides, and I will also stop recording. So I would like to thank all of you once again for joining, and we hope to see you next time in November.